Welcome to the Explainer. So today we're going to build a kind of chemical toolkit. We're going to use it to understand this really fascinating and honestly vital family of molecules. And they're literally all around us. I mean, in our food, even inside our own bodies.
So what do the smell of almonds, the structure of hormones, and the stuff in nail polish remover all have in common? I know, it sounds like a riddle, right? You've got this fragrant chemical, a super complex biological molecule, and a common household solvent. But the answer, well, it all comes down to the one fundamental building block they all share.
And there it is. They all belong to a crucial family of molecules, carbonyl compounds. So today, that's what we're doing. We're going to break down exactly what they are, we'll see how they react, and we'll even learn how chemists play detective to figure out which one is which.
All right, first things first. To get a grip on this entire family, we've got to start with the one single feature that defines every single one of them. Think of it as their basic blueprint. This right here is the heart and soul of every single carbonyl compound. You've got a carbon atom that's double bonded to an oxygen atom. That C double bond O, that's the carbonyl group. It is the star of the show. And pretty much all the chemistry we're about to talk about, it's all dictated by the unique properties of this little group. You know, what's amazing is how one tiny little difference in what's attached to that main carbon creates two totally distinct subfamilies. Okay, so if that carbonyl carbon is bonded to at least one hydrogen atom, we call it an aldehyde. But if that same carbon is sandwiched between two other carbon atoms, well, then it's a ketone. And trust me, this whole aldehyde versus ketone thing, it is absolutely crucial. We're going to see why in just a minute. Okay, to really get these molecules, we have to dig a little deeper. We need to uncover the secret personality of the C double bond O itself. Because it's not just a simple connection, you know? There's this hidden imbalance of power, and that is the master key to everything that happens next. So the secret all comes down to this one concept called electronegativity. The easiest way to think about it is like an atom's greed for electrons inside a chemical bond. And let me tell you, when it comes to being greedy for electrons, oxygen is a top contender. It's one of the greediest atoms out there. So because oxygen is so darn electronegative, it basically hogs all the shared electrons in that C double bond O. It just pulls that whole electron cloud towards itself, which means the sharing is totally unequal. And this is what makes the bond polar. You get a slightly negative end over by the oxygen and a slightly positive end over by the carbon. And that right there, that's the whole secret. That carbonyl carbon is now what we call electron deficient or, well, let's just say it's electron hungry. It's sitting there with this slight positive charge, which makes it an absolutely irresistible target for anything that has a negative charge or some spare electrons to share. Honestly, this one single fact is the key to understanding pretty much all of their chemistry. It's that important. Okay, so now that we know what they are, let's head over to the assembly line. We're going to see how our chemical toolkit lets us build these things from scratch. And usually the most common starting materials are their close chemical cousins, alcohols.
So to make an aldehyde, you have to start with what's called a primary alcohol. That's just a fancy way of saying the alcohol group is on a carbon at the very end of a chain. You gently oxidize it, but here's the catch. You have to get that aldehyde out of there the second it's formed, usually by distilling it. Why? Well, if you leave it in there, it'll just keep on reacting and oxidize even further, turning into something completely different, a carboxylic acid. So yeah, it's a pretty delicate operation.
Making a ketone, on the other hand, is way easier. It's much more straightforward. You start with a secondary alcohol. This time the alcohol group is on a carbon stuck in the middle of a chain. You add a good, strong oxidizing agent, and you just heat it up. See, ketones are a lot more stable, so you really don't have to worry about them overreacting like aldehydes do.
All right, time for the master tool in our kit. Remember that electron-deficient carbon atom we talked about? The electron-hungry one? Well, because of that, it's like a magnet for anything that's rich in electrons. And this fundamental attraction, it's the basis for the number one most important reaction for all carbonyl compounds. And that reaction is called nucleophilic addition. It sounds complicated, but it's not. A nucleophile is just a molecule that is attracted to positive charges. It loves the nucleus, right? So it attacks that slightly positive carbonyl carbon. And the addition part? That just means the nucleophile literally adds itself right across that double bond, and in the process, it breaks one of the bonds.
So let's walk through it step by step. First, boom, the electron-rich nucleophile attacks that electron-hungry carbon.
In response, the C double bond O, well, one of those two bonds just snaps. And the electrons from that broken bond, they jump up onto the oxygen atom. For the final step, that new negatively charged oxygen just grabs a proton from somewhere. And bam, just like that, you've built a totally new, bigger molecule. Pretty cool, right?
Okay, let's switch gears. Imagine you're in a lab. Someone hands you a vial with some mystery liquid and says, "This is a carbonyl compound. Figure out what it is." Is it an aldehyde? Is it a ketone? Well, it's time to open up our diagnostic kit and do a little chemical detective work with a few classic lab tests. Our very first tool is a total classic. It's all about elegance and a really clear visual clue. In fact, it's so cool looking, they call it the silver mirror test.
So Tollens reagent is a really mild oxidizing agent. It's got just enough oomph to react with aldehydes, but it's too weak to do anything to ketones. And that's the key. When it reacts with an aldehyde, it turns silver ions in the solution into actual metallic silver. So you get this gorgeous silver mirror coating the inside of your test tube. It gives us this fantastic, clear-cut way to tell them apart. Aldehyde, silver mirror. Ketone, nothing happens. Simple as that.
All right, tool number 2. This is another test that uses a different visual signal to help us figure out our suspects. This one is all about a really dramatic color change, from a bright blue to a brick red.
Okay, now this is where our detective work starts to get really interesting. Felling's solution, just like Tollens, reacts with aldehydes, but not ketones. But it's a bit pickier. It only works for what we call aliphatic aldehydes. You know, the ones made of simple carbon chains. It does not work on aromatic aldehydes, the ones that have a stable ring in their structure. So, think about it. If you get that brick red stuff, you know for sure you've got a chain-like aldehyde. But if it stays blue, well then it could be a ketone, or it could be one of those ring-based aldehydes. See how we're narrowing it down?
Our last diagnostic tool is a little different. It's not a general test for all aldehydes or all ketones. This one is a specialist. It's brilliant at sniffing out a very specific structural feature right next to that carbonyl group.
This is the ioform test, and it only gives a positive result. You'll see this pale yellow solid form if the molecule has this very specific structure. A methyl group, a CH3 group, right next to the carbonyl. So this test is amazing because it lets us zoom way in and identify a very particular kind of ketone. It's a super specialized tool in our detective kit.
And here is where it all comes together. Think of this chart as our ultimate carbonyl ID guide. Let's just walk through an example. Say you've got your mystery unknown. First thing you do? Tollens test. You get a silver mirror? Okay, right away you know it has to be an aldehyde. You can completely ignore the ketone columns now. Next, you run Felling's test on it. If it turns that brick red color, boom, you've narrowed it down. It's an aliphatic aldehyde. If it stays blue, well, then it must be an aromatic one. You see the logic here? It's like a flowchart. But what if that first Tollens test did nothing? Well, now you know it's a ketone, so you move on to the iodoform test. You see that pale yellow stuff form? You found a ketone with that special methyl group. No yellow stuff? Then it's just some other kind of ketone. By combining these simple visual tests, you can logically figure out the identity of your unknown. It is pure chemical detective work.
So what's the big takeaway here? It's that by understanding just one simple principle, that tiny little imbalance of power in the C double bond O, we've basically unlocked an entire field of chemistry. Just from that, we can predict how these molecules are made, how they're going to react, and even how to tell them apart. And that really brings us to a much bigger, more fascinating question. Now that we have this toolkit, where else can we see these exact same fundamental reactions playing out? From chemists synthesizing brand new medicines in a lab, all the way to the incredibly complex chemistry that's happening inside our own cells right now.